everybody. My name is Linda Liu.
My name is Riley Silva.
I'm James Melvin.
I'm Venkat Vetsa.
I'm Corey Dixon.
And this is our senior design project, H2Eyes. Swimming is a common mode of exercise for those with visual impairment. However, it is difficult for those with visual impairment to navigate a pool independently and efficiently. Lane dividers, as you can see in the image, are used to assist visually impaired swimmers. However, they can frequently crash into them when they stray off course. Using the dividers as a guide is inefficient as it slows down the swimmer when they collide with the divider. Assistance for visually impaired swimmers is minimal and relies heavily on the pool's environment and sighted assistance. Our project goal is to help swimmers gain independence by designing an easy-to-use device that will allow them to swim straight within their lane. We designed a device that helps a broad range of users, from performance-oriented athletes to casual swimmers who rely on sighted assistance and lane dividers to help them guide them through their lane. This device can also be used for orthopedic training.
To help visually impaired users navigate within their lane, we decided to use computer vision because it requires minimal setup for the user and no modification to the pool. By aiming a camera downward, we're able to track the black lane line at the bottom of the pool to guide our users. Our physical design resembles a kickboard, as kickboards are already widely used by swimmers. All the electronics are housed within the main body of the kickboard. Vibration motors for user feedback are embedded within the handles, and the handles make it easy to ensure the user holds the device correctly. We quickly realized that the motion of swimming causes the user to rock the kickboard back and forth, which is a problem when trying to determine the location of the line relative to the swimmer. To solve this, we added an inertial measurement, or IMU, to account for the angular displacement of the camera. And here is our anticipated usage environment for our device. As you can see, this is a standard lap swimming pool, and it has these black lane lines running along the length of each lane. And then here's a quick video demonstration of our initial prototype, which we were able to test in a pool. You can see that our computer vision is detecting lots of lines, but that the footage is also very shaky due to the swimming motion.
So as Corey pointed out in the last slide, our computer vision algorithm detects a lot of lines when we run it. And this is great because we can have a lot of reference points. However, it causes problems if there are extraneous features on the bottom of the pool, such as tiles to make up that black line or a sharp shadow that's not at the same angle to our line. We had to build a custom filter that analyzes each line and chooses the one that is most similar to the feature we have been tracking. This does this by analyzing each line in the world frame and comparing it to where we think the line is. On this slide, you can see we have two images. One on the right is an actual image taken from our device looking down at a line, and the one on the left is a rendered kind of simulation of the geometry that we're looking at. On the left, you can kind of see the gray transparent area is the field of view of the camera, and that black line is the line that we are trying to track. Now you'll notice there's a couple of features painted on to each of these images. There's a blue dot, which represents the projection of our device down onto the bottom of the pool. We obtain this by taking a reading from the IMU of the direction of gravity and projecting that downwards. There's also a red line that represents the edge of the line that we're trying to track. We obtain this by finding the line using our computer vision algorithms, and then taking each endpoint and again projecting it down on the bottom of the pool. Once we've projected all three of these points down onto the bottom of the pool, we can eliminate a dimension and solve a two-dimensional problem of the swimmer's position relative to the line. We do this by simply finding the point on the red line that is closest to the blue dot, and you'll see this represented as the green vector in each of these slides, or each of these pictures. The magnitude of this green vector determines the amount of feedback that we give our user, and its direction, i.e. If it's on the right side of the line or the left side of the line, determines which direction we want our user to turn. Here's a quick demo demonstrating our ability to resolve the orientation of the device relative to the line. You'll see as I tilt the device up and to the side, the green correction vector in the upper right-hand corner, which is what the device sees, doesn't change very much. It is wiggling a little bit, but that's mainly because I couldn't hold the board perfectly steady as I was tilting it. This demonstration proves that we're able to resolve the attitude of the board and correct for its location in 3D space.
Here's a circuit diagram of our system overview. There are two major subsystems within our design, the first of which is a computer vision subsystem, which is comprised of a camera and a Raspberry Pi, and the second is a attitude estimation subsystem, which is comprised of an Arduino Pro Micro and an MPU 9250 IMU sensor. Other components that you can see in the circuit diagram are a power supply, which consists of a 12-volt battery and a 5-volt regulator, as well as a motor driver and vibration motors, which are used for haptic feedback. Here's a picture of our most recent prototype. It has all the components that were outlined in the last slide and a couple additional ones, mostly being a screen, which is used for debugging purposes, as well as LED indicators, which are used purely for demonstration purposes. As you can see in our next couple of videos, they indicate what the device is going to be doing and how it's going to be directing the user.
Here's an overview of the software flow of our current prototype. The device is split up into two subsystems, the Raspberry Pi and Pro Micro. They act together in a master-slave setup, with the Raspberry Pi acting as the master and the Pro Micro acting as the slave. The Pro Micro deals with interfacing with the IMU and microcontroller. So this allows the Raspberry Pi to focus its computational power on processing frames as fast as possible. Here is a demo video of our current prototype in action. On the left is the device, and on the right is a capture of what the device sees. As the device moves back and forth, you will see the blue dot cross the red line on the right video. As this happens, the green correction vector also changes along with it. As the dot continues to move across the red line, the LED in the left video swaps colors, indicating that the swimmer needs to change directions. In this demo video, the LEDs represent what the motors would be doing and what a user would feel.
Our goal was to address the issues that visually impaired swimmers face and develop a device that can provide them with the assistance that allows them to swim independently. Using computer vision and attitude estimation, we succeeded in being able to direct the user so that they can follow the lane line on the bottom of the pool without the assistance of another person. This allows a visually impaired swimmer to enjoy swimming without the help of someone else. Our project proves that this is a feasible approach to assisting visually impaired swimmers, and the core technology that we developed can be adapted towards a wide variety of use cases and give swimmers the confidence and independence they need to exercise on a regular basis. Thank you.
Okay, thank you, team. Did you have a chance to actually test this with in the pool with actual users?
Unfortunately, due to circumstances out of our control, when we started making our more defined prototypes, we weren't able to contact users because of the whole pandemic thing.
Or did one of you try it with your eyes closed or something?
We did end up testing it in the pool ourselves. I believe, Corey, you're the one who did that, right?
Right. Well, so the one we tested was we were mainly doing preliminary testing to see if our sensor systems were working properly, and we hadn't reached the point in the project where we had added the haptic feedback function to our prototype yet. So that was something we were doing during spring quarter while all the pools were closed, unfortunately.
Once we had a refined prototype, we were all split up and weren't able to test in that fashion.
Okay, well, unfortunately, the pandemic didn't spare anyone, but very nice work, and I hope that you will have a chance